So thank you all for being here. It is a real pleasure to see everyone in person. And for those following online, we welcome to you as well. Really appreciate you all being here. Hopefully this thing is behind us and we can take it onwards and upwards from here. This is an exciting stage in the growth of gallium nitride, the next generation semiconductor technology. The information discussed today is qualified in its entirety by the Form 8K filed with the SEC today and may be accessed on the SEC website and also via Navitas-Semi.com. A video recording of today's presentation will be available shortly. Please review the disclaimers included in the filing. Statements made during this call that are not statements of historical facts or otherwise constitute forward-looking statements, are subject to risks, uncertainties, and other factors that could cause our actual results to differ from historical results and/or from our forecast. Do not place undue reliance on forward-looking statements for which we assume no responsibility for updating. After the main presentation, we will have a series of exciting customer presentations and then Q&A. We will alternate questions from those in person and those online. If you are online, please use the chat function on your laptop. Now, let's learn about gallium nitride in a short video, and then we'll welcome Gene Sheridan, our CEO.
Okay, great. Well, thank you everyone for joining us. It's a big day for Navitas, our first Investor Day, first of many to come, and I think very much one of the first hybrid events that the NASDAQ is putting on. So thanks to all of you that are here in the audience, as well as everybody zooming in from around the world. I wanted to hit a few of the high points, and then we're going to introduce a number of speakers to talk through some of the key developments and the opportunities at Navitas. We are starting with gallium nitride technology. We're going to tell you all about it, but we view ourselves as the next generation power semiconductor company, a company that's going to change power electronics and power systems for decades to come. Gallium nitride is a very powerful material, as you saw in the video. It enables power electronics, power systems to be up to 3 times smaller, lighter, faster weight, 40% energy savings, and ultimately lower cost. We do it with a unique GaN power integrated circuit. Others are making GaN discretes. We'll tell you all about the merit and benefit of a GaN power IC and how that unlocks the full potential of GaN in power systems. We're off to a great start with the #1 market position in this early market. Over 140 GaN chargers in production, over 24 million units shipped without a single failure, all of this protected by over 130 patents issued or pending. It's just the beginning. This is chapter 1. There's a lot of fun chapters ahead. It's a $13 billion electrification opportunity for GaN. Most of that is dominated by silicon. That's going to change dramatically in the next 5 years. We're starting with mobile and consumer, a fast-moving, simple value prop we'll tell you all about. You're going to see those 140 GaN chargers later with demos, but we're going to quickly move into 3 expansion markets: enterprise, sustainability, and electric vehicle or e-mobility. GaN IC is an incredible financial opportunity. It's also an incredible energy-saving opportunity. With every GaN chip we sell, it is a 4 to 10 times smaller carbon footprint than the silicon chips it replaces. We go into all of these end markets, and by 2050, we could impact up to 2.6 gigatons of carbon reduction by 2050. These are very big numbers. It's a very big opportunity, and we're equally excited about the financial opportunity as we are about the climate impact that we can have for our planet. It's a real pleasure, personally. Much of this management team are people that I've worked with for 25 years, not the 8 years or 7 years since we started the company, but 25 years. Some of the top people in power electronics and power semiconductors, a cumulative experience base of over 300 years. We have built products, we've built technologies, we have built businesses together, but this is definitely the biggest achievement and will be the biggest achievement of our careers over the next 10 years. All of this has come together, create really strong pipeline of opportunities, but not just a pipeline, real revenue. Real revenue last year at $12 million, this year doubling, nearly tripling. Next year doubling or tripling again. We're off to a great start, but it's the tip of the iceberg of big things to come. So with that, let me give a little bit more detail before I introduce some of the other speakers. Silicon has been the workhorse. This is what we used for the last 30 years to build power semiconductors and to build power electronics. It was pretty good. It had its run. It's commoditized, not very exciting, not a lot of future performance gains, cost reduction gains. Gallium, when you combine it with nitrogen, forms an incredibly powerful bond, 10 times stronger electric fields, 2 times faster electron mobility. What does all that technical mumbo-jumbo mean? It means a really powerful chip to handle lots of volts and amps in a tiny size that is low cost, fast, and efficient. And if there's one theme, I know nobody here of our investor group are power electronics experts. There's one theme to learn, it's speed and efficiency. That's really the name of the game. And a GaN chip is the ultimate in speed and efficiency. 20 times faster, 3 times smaller, lighter weight, higher density, faster charging, big energy savings, as I said, and ultimately lower cost. Let me explain further about speed and efficiency. Why do they matter so much in power electronics? Speed on the left, efficiency and energy savings on the right. Power supplies are switching power supplies. The faster they switch, the more you can miniaturize the components inside the system. 50 to 70% of a power system are these big, ugly, bulky, passive components. They store the energy. If you switch slow, they need to store a lot of energy per switching cycle. Silicon traditionally switches slow. For 30 years, frankly, 50, 65 kilohertz. Slow switching means big, bulky, expensive passives. You'll see in the demos later, open up a power supply, they look like they were designed in 1972, because they pretty much were designed in 1972. Lots of discrete components, big, bulky passives. This is going to change dramatically when you can get away from slow switching silicon. And I know you think silicon is fast switching in processors. These are high voltage, high power supplies. Using silicon to create high voltage, high power supplies has not been ideal for 30 years. Slow switching, big, bulky, expensive power supplies. GaN has the potential to change all of that. You'll hear us talk a lot about GaN discrete and GaN IC. GaN discrete simply means a single function transistor. The transistor is a core ingredient to switching a power supply. GaN discretes get you going faster. When you go faster, you shrink those passive components, start to miniaturize them. But GaN discretes have some limitations that we'll explain. Ultimately, our GaN IC that we invented nearly 7 years ago unlocks that full potential, not a few hundred kilohertz, up to a megahertz or more, dramatically miniaturizing these passive components. These are capacitors, inductors, transformers, filters, and the like. All of them shrink down. So speed is the key to reducing size, weight, and ultimately a large part of the cost. Efficiency is a little easier to understand. A power supply is never 100% efficient. It is moving, distributing, and converting energy. It takes work to do that. Work is going to burn up that energy in the form of heat. Traditional silicon-based power supplies are about 85% efficient. That means 15% of the energy is used up in moving the energy, distributing it, converting it. When it burns up that energy, it burns it up as heat. Heat is the enemy of reliability in electronics. When things run hot, they wear out faster, especially true in semiconductors. So we have a lot of motivations, obvious motivations for higher efficiency. 95% efficiencies are possible with GaN. That means we're getting the energy to work, whether it's moving a car, cooking your food, lighting up the lights, or powering your phone. We want to put that energy to work and not waste it as heat. We can move from 85 to 90% to 90% typically with GaN discrete. But again, here, our invention of a GaN IC unlocks the full potential, 95% and sometimes more efficient. What does that mean is 20 to 40% energy savings compared to traditional silicon power supplies. But again, cooler temperatures, better reliability. On top of it, a GaN IC integrates lots of things, including protection circuits, built-in protection. This is something that silicon never had and GaN discretes don't have. So you've got a double benefit in improving that reliability, up to 100 times better reliability. Now let me go a little deeper. Why is that GaN IC so good compared to silicon, but also compared to GaN discretes? We show in the upper row traditional silicon discretes. The discrete transistor is shown in the middle, the power device. That's a symbol for the transistor, or FET, field effect transistor. Silicon was slow. You need a driver to drive that transistor, shown here. Traditionally, that's been a standalone driver or built into a system controller. At low frequency, it doesn't matter, but there's a lot of parasitics. What is parasitics? It's unintended resistance and inductance that slows down the speed and degrades efficiency, creates some of that inefficiency, that heat that we don't like. At low frequency, these parasitics that are inherent in the electronic design, the PCB design and the packaging, aren't too big a deal because you're switching slow. So they're not slowing you down very much. But as we want to unlock the full potential of GaN to switch at megahertz range, these parasitics really matter. The other thing that matters is the silicon driver has to switch just as fast as the power device. So if I give you a great power transistor in GaN, but I don't solve the parasitics, you're forced to use a complicated silicon driver, which is limited to the same speeds of 65 kilohertz or 100 kilohertz in the past, we have a problem. This has been a problem for the last 20 years of people doing early work in GaN. When we started our company, we knew if we didn't solve this problem, we would unlock the full potential of GaN, and this commercialization of GaN would never really occur. That's the beauty of a GaN IC. It actually integrates the silicon driver into the GaN chip. It eliminates parasitics, so there's no delay, there's no inefficiency. And the driver and the transistor are now perfectly tuned and matched to take advantage of the GaN material, the fastest, most efficient switch and power device possible. In a nutshell, this is a GaN IC. It also gives you the benefit I said before of built-in protection circuits for even higher reliability on top of that, better efficiency and cooler temperatures. What does this all mean? I know it's very technical. At the end of the day, it's about the products. We're delivering a lot more power in a lot smaller size, a lighter weight, higher energy efficiency. Don't waste that energy. Don't create the heat, and ultimately a lower cost. And it's shown in all the examples we might give today and in the demos later, whether they're silicon chargers or products or even GaN discrete products. Let me give you one more real-life example to try to bring it to life while still translating this to some of the technical concepts. Here we're actually comparing a GaN discrete design on the left compared to a GaN IC design on the right. If I showed you a silicon one, it would be even bigger and less efficient. The GaN discrete is embedded inside this MCM, multi-chip module. Why do we call it a multi-chip module? Because this supplier chose to integrate a couple of the system chips that you see in blue on the right are actually integrated, which is why it's bigger, because it houses some extra system chips. Integrating those system chips does not create any performance advantage. It's a small convenience benefit to the customer. But more importantly, Embedded in here is a discrete GaN. It doesn't solve the silicon driver problem. It doesn't solve the parasitics problem we talked about. As a result, it switches slow. In fact, the same speed that silicon has switched for 30 years. Why does that matter? The real action is not here on the GaN side. It's on, flip the board around. It's on the passives. Remember what I said, the passive components are 50 to 70% of the size, weight, and cost of most power systems. These things, because you're switching slow, are still huge. These are all those inductors, transformers, filters, capacitors added up. And as a result, you really don't shrink the size. You're not getting the power density benefit you would like from GaN. Contrast that to the GaN IC, has the driver built in, has the protection circuits built in. Now we're switching 6 times faster. Those yellow and orange circled passives have dramatically shrunk down. From a top view, you can see it's about half the size. Look at the profile. This is an OPPO charger, one of the fastest growing smartphone companies in the world, where we co-developed this product. Incredible size and weight, the thinness of almost like a cookie. In fact, they call it a cookie charger over in Asia where it's developed. The result here, 6 times faster switching, use a GaN IC, 3 times smaller in size, or we say 3 times higher power density. 3 times the power in much less size, or cubic centimeters. A dramatic difference, again, not just to traditional silicon, but to any alternative that might use GaN discretes. With that, I want to introduce to you my co-founder and very good friend. Dan Kinzer and I have been building technologies, businesses, products. I would like to say from the 80s, he might be more like the 70s. But we partnered up in the mid-80s. In fact, we led the first gallium nitride investment at IR, where we worked for 2 decades or more, in the early 2000s. So this company is not 7 years old. We've been working on this technology for over 20 years, and we've been building great business and technologies for 25 years. And it's been a lot of fun, and we're looking forward to even more fun in the next 10 years. So welcome, Dan.
Thank you, Gene. Thank you very much for that introduction, and thank you for that great introduction to the topic of GaN and GaN power ICs that we've been working on for the last 7 years together at Navitas. And in that 7 years, we've developed quite a few things. But in particular, we've developed a lot of intellectual property, which of course is a very key element in every company. It started with that amazing GaN transistor, the 650 volt E-mode power FET that we make. Enhancement mode transistor is the core of every one of our chips. It's the most efficient transistor there is, 20 times faster, as Gene said, very small, 3, 4, 5 times smaller than the silicon chips that it replaces. But in addition to that, and because we recognized early on that GaN transistors need very special control circuits, and it's best to put those control circuits right on the chip next to the power device, because then nothing gets in the way. Nothing is in between the driver and the device that it's driving. So we started developing a whole kit of over 20 devices, passives and actives, in different voltage categories and different power ranges, signal devices and power devices, so that we could integrate lots of things. And we followed that, of course, with characterizing each one of those devices to develop very accurate models of all of those devices, so that then the guys that are developing the circuits and libraries of components that we build into our chips can be confident that the devices will perform as expected. And we can develop all that list of analog and digital circuits, which we then combine into products. And in the course of doing that, we've invented a lot of things. So we do have over 130 patents issued and pending. And as a result of this, and because we were a very early company trying to do this, really the first one commercializing these power integrated circuits, we have an intellectual property position that it's virtually, I won't say impossible, but very, very difficult to make a GaN power integrated circuit that has high performance, low power loss that our devices do without somehow crossing the intellectual property that we've created in this process. And of course, it's relevant not just for the consumer applications that we're highlighting here today, but for the various other target segments that we have. And it's not just limited to devices, it's not just limited to circuits. We've patented the packages that we put our parts in and the systems, some of the system topologies that people use as well. So in building our product, we follow this relatively simple flow. We start with a very low cost, the lowest cost perfect crystal substrate you can start with, a silicon wafer, highly available, very common, very low cost, nothing exotic there. We then take a tiny amount of GaN, of gallium, combine it with nitrogen in an epi-layer growth process, which is done in a commonly available reactor, and a reactor that we can scale in volume. And those reactors are getting better and better in terms of delivering higher performance per unit cost. So we are working with vendors on that as well, and with our supplier. And it took that supplier, TSMC, for our wafers, we've been working with for quite a long time, over 10 years. I've been working with TSMC. Since the beginning of our company, we recognized that they would be a great manufacturing partner, and we've worked together and helped them, and they've helped us to improve the manufacturability of the product, the reliability of the product over those years, and continued to drive down the cost structure. So as a result of that, we've been able to achieve these kinds of yields, over 90% from starting wafer to out the door, and this kind of demonstrated field performance with no field failures. The other advantage is that unlike some of the silicon devices that we're replacing, we have capacity, we have relatively short lead times, and as many of you know, the silicon market is very oversubscribed right now, and we have room to grow. I'd also like to mention our packaging with Amkor. That is highly scalable, and we have other partners as well. So we've adapted the industry standard packaging process to make specific high voltage and high power packages for GaN, which are also patented. So in doing this, how can we lower the cost? You see that a few years ago, it would have been extremely expensive to try to integrate GaN into a power system. But here where we're sitting today in 2021, the price of a system, the cost of a system to integrate GaN is coming down very, very close to that of a silicon system. Still a little bit higher, a few percent higher, but we're anticipating a crossover in the cost of a system over the next 1 to 2 years. And within another year or so, actual crossover in the cost to make a GaN transistor to fulfill a given function. So we're moving the bar in cost. We're doing that because we've been doing it for a while, as Gene said. We started looking at this field 20 years ago. We're very familiar with it. We spent 7 years improving yields and manufacturability. In addition to that, we're working with our partners to develop a new GaN generation every year. We're on our 4th generation now, and 5th generation will be coming. So in addition to that, more and more functions and features are going to be integrated into our products every year, lowering costs for the customers to implement. And as we do all that, we'll keep driving the frequency up. We'll go faster and faster, making those passives Gene showed you smaller and smaller. Another big benefit is that, you can see it right there, we put milligrams of the raw material GaN into our integrated circuit, and we save kilograms of CO2 emitted into the environment for every part that we ship. So this is a big part of our company's objectives, to be a company that can move forward the efforts, the worldwide efforts to cut carbon emissions, to mitigate climate change effects. If you look at our component itself, just the chip, we consume 4 times, or we cause the emission of 4 times less carbon than silicon chips do. And it's going up to 10. It will be 10 with our 4th generation product next year. We also, because you can use these smaller passives, the smaller transformers, inductors, capacitors, in the chargers, they have a smaller footprint, almost a third smaller footprint overall in carbon emissions. On a bigger scale, by implementing GaN and the efficiency improvements that it can bring to electric vehicles, we believe, and analysis has shown, that we can accelerate the adoption of electric vehicles by up to 3 years, which would save 20% of road sector emissions when combined with our high efficiency performance of gallium nitride by the year 2050. So in that year, the GaN technology that we are working on, we believe can address 2.6 gigatons per year of carbon emissions. What does that mean? The world needs to cut carbon emissions by 25 to 30 gigatons. So there's 10% of the problem. So with that, I'd like to turn it over to Dave Carroll, our Worldwide Sales Senior Vice President. And there you go.
Not quite as tall as Dan and Gene here. Thank you very much, Dan, and good morning, everyone. I'm going to start out with an overview of the mobile charger market. We chose the mobile charger market as our first target market because the value proposition is quite simple and very compelling. The market's very large, and the industry moves very quickly to new technologies. The trends in mobile devices are clear. Larger screens, more powerful batteries, and processors result in mobile devices that are very power hungry and can take 3 to 4 hours for a complete charge. GaN ICs enable up to 3 times more power and therefore up to 3 times faster charging in half the size and weight of traditional silicon chargers. The market is actually quite large, 2.5 billion mobile chargers shipped every year. And with the potential for $1 of GaN content per unit, this is a $2.5 billion market opportunity. The value proposition becomes even more compelling when you integrate multiple chargers into a single device. As you can see here, there's three silicon chargers, big and bulky, and they can be replaced with a single multi-port GaN charger, which is 3 times smaller, lighter, and actually less expensive than the chargers that it replaces. It's obviously a lot more convenient as well. When we launched our first GaN ICs in late 2018, we saw aftermarket players quickly launching new products. By the time we got into 2019, we'd seen dozens of new GaN chargers coming to market from leading brands like Amazon, Baseus, Aukey, Belkin, and Anker. Last year, Tier 1 OEMs began launching GaN chargers, many of them in-box models that ship inside the box with the mobile device. Today, our customers include leading Tier 1s like Lenovo, Dell, LG, Xiaomi, OPPO, and others. We now have over 140 chargers in mass production, another 150 plus in development for deployment in the coming 18 months. We can't talk about products that have not yet been announced, but we can tell you that we're working with more than 90% of mobile OEMs on new GaN-based charger products. We've shipped over 24 million units without a single failure, giving our Tier 1 customers high confidence in our quality and reliability. As I mentioned, we now have over 140 GaN chargers in mass production. Based on publicly available information, we believe this is more than all other GaN companies combined. While we do compete with other GaN companies, our primary competition remains silicon. That's really our focus, is how can we drive all of these chargers to moving from silicon to GaN. And as Dan mentioned, we're driving that cost down, getting to silicon cost parity and below, paving the way for all these chargers to move from silicon to GaN going forward. And these trends only continue. You can see Tier 1 mobile OEMs announcing ever higher power platforms, moving from 20 watts to upwards of 120 watts, driving the need for these GaN IC-based solutions. In fact, 8 of the 10 platforms shown here are based on Navitas GaN ICs. Now moving to the non-mobile part of the consumer electronics market, we're focused on devices that need higher power in smaller and slimmer sizes. Specifically, we're talking about ultra-thin LED TVs, gaming systems, all-in-one PCs, and smart home devices. GaN ICs make this possible. You can pack up to 3 times more power in the same size and weight in the same form factor, or make it 3 times smaller and lighter, and at the same time save energy. We've established our lead customers in 2 of these segments, including a Tier 1 LED TV that is set to launch later this year, and a Tier 1 all-in-one PC also planned to launch later this year. Again, this is a very large market. Over 600 million systems ship each year. With the potential for $3 of GaN content per unit, this is another $2 billion market opportunity. And with that, I'm going to hand it back to Gene to talk about our higher power expansion markets.
All right, thank you, Dave. So that's pretty exciting. Mobile and consumer alone, $4 billion GaN opportunity. Clearly, as a company at our stage, we could have just focused on mobile and consumer. And I think the potential and expectation is for hundreds of millions of dollars over the next 5 to 10 years in those 2 segments. Very tempting. In fact, we debated it heavily before deciding to move forward on the IPO. And a major consideration for the IPO was to attract additional capital to leverage the full potential into additional markets for GaN IC. So I want to tell you about these 3 market expansion areas. We're just getting started. Product developments have started. Customer engagements have started. We'll be launching the first commercial samples of the GaN ICs into 3 new segments by the end of this year. Let me talk about those segments one by one. First, data centers. Data centers are famously a big power hog. Nearly 50% of the cost to operate a data center is related to power. Cost of the power supplies, cost of the cooling, and cost of the electricity itself. Data centers are famously inefficient. A silicon-based data center today is only 75% efficient. That means 25% of the energy going in gets burned up as heat and never reaches the data processors, which is the whole point of a data center. That's a real travesty. Gallium nitride can cut that energy waste by about 35% or about 10 points, bumping a GaN-based data center to about 84% efficient. When the whole world moves to GaN data centers, and I believe they will, that will save nearly $2 billion in annual electricity costs alone. But that's only a part of the picture. If you burn less energy up, you create less heat, you'll spend less money on cooling. That is not factored into the numbers. And believe it or not, power density matters. You think a data center is huge, every square foot matters. In the racks where these power supplies go, today, nearly half the rack is for power supplies. The other half is data processors. By shrinking the size, in the example given on the lower left, we can deliver the same 3,000 watts in this example in half the size. That means less footprint in the rack is dedicated to power processing, so we can dedicate it to data processing. In the end, that's the goal of a data center. So this is a great example of big savings on energy, electricity costs, big benefits on cooling, but also big benefits with power density. We've already lined up our first customers. As I mentioned, we're developing the lead commercial samples now to deliver to them in Q4. Luckily, many of the same consumer and mobile customers that Dave was referring to are also playing in this space. We know them well. They're anxiously waiting the samples to start commercial development and scale up again at the end of this year. Let's look at the second market, solar. If you boil down solar, it's really all about cost per watt. What's the cost to implement the hardware to implement solar, and how much free energy or free watts am I going to get to pay back that hardware cost? Cost per watt is what GaN is really good at. While we can't make the panel itself better, we can make dramatic gains in the number 2 problem, if you will, in terms of efficiency and cost, which is the inverter. Inverter is just the name in solar for the power supply. It takes the energy from the panel and converts it to your house, back to the grid, to energy storage, to charge your EV. We can make huge gains with that inverter. We estimate 25% lower inverter costs using GaN in the next few years and a 40% or greater energy savings. Put that together, our estimate is we can improve the solar payback. How fast do I pay back that hardware installation? By 10% or more over the next few years. This is a huge opportunity, fits like a glove for GaN. We've already identified our lead customer who's already committed to move from silicon to GaN over the next few years. That customer alone is over $500 million of GaN revenue for Navitas, potentially, when it would start in 2023 over the subsequent 7 years through 2030. And in total, we estimate the GaN market here conservatively, just solar residential actually, not even counting solar farms and larger scale implementations, to be over $1 billion per year. And third, and probably the biggest, but it will also take the longest to commercialize, is electric vehicle. If you think here, what is holding back EV adoption? I would argue there's 3 factors. EV cars are still a little bit more expensive than their gas counterparts. Drive range anxiety is still a major consumer concern. And where you're going to get your next charge and how fast is that charge going to come. 3 factors. GaN can play a big role in all 3 factors. In the car picture on the upper right, GaN is mainly used in 3 areas. The onboard charger, that's a natural one. Just like we can fast charge a phone, we can fast charge a large, high-power, high-voltage battery in your car. But once you get the energy on the battery, you got to take it off. That's the high-voltage DC to DC to convert that energy from the battery to power the rest of the electronics in the car. And then the other big one is the electric motor or traction drive, where you're converting that energy into moving the car. GaN plays a big role in all 3. In fact, our first lead customer is focused on the onboard charger and the DC to DC converter. Here again, they've already decided to move from silicon to GaN for their next generation designs, and the impacts will be significant. This is today's benchmark onboard chargers, even in a Tesla, are around 6,000 to 7,000 watts. It sounds like a lot of power, but it's actually pretty slow charging. When you charge at your home, it can take up to 10 hours. Overnight, that's fine, but not everybody has 10 hours to charge your battery at home. We're developing an onboard charger that is 3 times more powerful, about 20,000 watts, 3 times faster charging, and about the same size and weight or less than the one it's replacing. That is huge. It's a $400 million GaN revenue opportunity when it would start in production in the 2025 timeframe. That alone is $50 of content at 50 million cars, $2.5 billion potential. But then there's still the DC to DC converter, and there's the traction control or electric motor as opportunities. Once the entire power electronics moves from silicon to GaN, not only will we dramatically improve the charging time as I described, but actually our estimates from key customers that helped us develop these estimates are that all that energy savings will ultimately translate into a significant savings on the battery, on average about $500. Those are big numbers. Again, getting the cost of an EV ultimately to the same cost of gas cars or less, but also conversely extending that driving range by 5%. Every 1% is extremely hard to come from in the EV space. So 5% for one technology change is, of course, a big deal and an exciting improvement. So let's come back to the bigger picture. The market opportunity today for these markets we target in silicon is about $9 billion last year. GaN is in its infancy, maybe $20 million, mostly from Navitas last year. The overall market projected to be $13 billion. The GaN projection by third-party estimates is expected to be $2 billion of that. That's an exciting growth going from $20 million to $2 billion in just the next 4 or 5 years, doubling every year. That's extraordinary, but keep in mind it's only 15 to 16% of the $13 billion potential. That $2 billion will also be nicely diversified across the 5 segments we talked about. Mobile and consumer going first, but data center or enterprise, renewable and solar, and EV and e-mobility kicking in significantly. Let's take a look at how those ramp in terms of our financial plan. Last year, as I said, $12 million. This year, $27 million, virtually all coming from the mobile charger space. Next year, ramping significantly, again, dominated by mobile with some of the consumer applications that Dave talked about kicking in, those thin TVs, all-in-one desktop PCs as two first examples of a much bigger consumer potential. And then although we're delivering the samples, the GaN IC commercial samples, I said, to all three expansion markets, solar, data center, and EV, they all kick in at different times depending upon the customer's development time. Data centers is typically 12 to 18 months from building first prototype to commercial production release. Solar tends to be 2 to 3 years. Electric vehicle tends to be 3 to 4 or sometimes 5 years. As such, you'll see in 23, enterprise and solar really kicking in there, strong growth into 24, and then we see our first EV revenues starting in 24 and ramping fast into 25 for a total $640 million plan. Again, this looks like an exciting growth trajectory, and it certainly is. This represents only about a third of that $2 billion. That $2 billion represents only about 15 or 16% of that broader potential $13 billion that we're really targeting. How does it look in the short term? I talked at the beginning about a total pipeline of $680 million. I want to give you a little bit more clarity on that. The awarded piece is about $100 million. By awarded, we mean these are production programs using our GaN IC either in production today or committed to go to production in coming quarters using Navitas GaN. That $100 million alone gives me great visibility and confidence to this year's $27 million and next year's $69 million. But on top of that, qualified opportunities are committed production programs that have high interest in the GaN, but they haven't made the final decision yet. That represents significant upside for us this year and next. And as Dan highlighted, we're lucky that our supply chain is so efficient and has actual significant upside to it that we can capture that in what is otherwise a very tight semiconductor industry. But also a big part of that $580 million are the early opportunities I defined in solar, data center, and EV that gives me great confidence in not only 22, but 23, 24, and 25. And finally, I want to introduce our head of finance, Todd Glickman. He's going to talk a little bit about our short-term and our long-term business model. Welcome, Todd.
Thanks, Gene. So, in combination with accelerating revenue growth, we're also accelerating our gross margins. While we finished the year of 2020 at 31% gross margins, we quickly transitioned to our second generation of technology and are on track to hit our 46% gross margin for 2021. In Q1, we closed at 44% and are, again, moving towards that 46% long term for 2021. However, that's only the first step in our process. Going from 21 to 26, we expect to expand our margins through 4 focus areas. First, we're going to develop new generations of technologies every 12 months. And these new generations will create a 20% generation over generation cost reduction, with the majority of this cost reduction being passed along to our customers because our ultimate goal is to drive that GaN premium to 0. Secondly, additional integration. Right now, we've integrated drive, control, and protection. However, we're just scratching the surface there. With each of these new generations of technology, we're going to add a new feature which will help simplify the adoption of GaN across all our end markets. And then optimize our supply chain as we move into additional end markets. And then as revenues ramp, we plan to drive our cost of materials lower, passing along that to our customers as a slight offset to ASP. But long term, we're here to go 55% margins. Now that is our choice. We believe that there is upside to go to a 60% margin long term. However, our goal is to drive adoption first and then margin expansion after we've converted a large portion of the market from silicon to gallium. Now, if we move to the upper left-hand corner, you're seeing that we have a negative EBITDA today. However, with the help of the $100 million in awarded customers in our pipeline, we expect to pass into a positive territory in 23 and then reach a very healthy margin of 25% by 2026, with the majority of our operating expenses allocated to research and development. Now, the great part is we can do all this with with zero capital expenditures. Today, we're operating with zero, and all the CapEx that you're seeing going forward is going to be related to a minimal amount of test and manufacturing equipment. But long-term, we are going to represent less than 5% of our revenue, allowing us to maintain our identity as a fabless semiconductor company. So with that, I'm going to hand it over to Rick, our partner at Live Oak, to discuss the transaction.
Thanks, Todd. I'm Rick Hendrick, CEO of Live Oak Acquisition 2, and as that name sort of indicates, it's the second SPAC that our team has put together. We are obviously thrilled to be here with Gene and his team from Navitas. We originally met Navitas in December. I think, in fact, our first meeting, Gene was in his Tesla doing a Zoom call with us. But we spent quite a bit of time here in advance of announcing a merger. I think I want to talk a little bit in a minute about just how we approach underwriting. But in terms of the transaction itself, all of the existing Navitas shareholders are rolling into this transaction. Included in their current investor base are firms like Capricorn, who many of you know is a very well-recognized sustainability-focused private equity investor, Atlantic Bridge, who has deep semiconductor experience, as well as a number of their customers as strategic investors. So all of them roll into the transaction. We have a $145 million pipe that was raised in what was honestly sort of a tricky pipe market. We were fortunate. We went out looking for $100 million and were able to upsize even in a difficult market. And I think that's great validation for how investors have looked at the transaction, the valuation, and the company itself. And then from a sponsor standpoint, we have chosen to really align ourselves with Gene and his team in terms of what the sponsor economics look like in this transaction. And what that really means is there is an earnout here for the Navitas shareholders that it's 10 million total shares, and it vests at $12.50, $17, and $20 a share, a third. We have deferred 20% of the sponsor economics to vest on those same terms. But we've gone really beyond that because we've taken the other 80% of the sponsor economics and gone into a longer than typical lockup alongside management. So both the inside shares that management owns and the Live Oak sponsor shares are subject to as long as a 3-year lockup. It's sort of a third structure with 1, 2, and 3-year periods. We think this is really the right way to be aligned, not just with our partners here, but with the market, right? And though the SPAC market has gotten much more difficult over the past several months, I think some of the reasons for that are that there isn't always perfect alignment between sponsor groups and public company investors, and so we've gone a long way here. We believe, and we hope everyone else believes, to be fully aligned with the market and the new investors, whether they are PIPE or public in nature. In terms of the valuation itself, it is at 5.7 times the 2023 revenue. You'll see on the next slide, we look at this as a very significant discount to peers. The peer valuation we worked off of 22 revenues, simply because not all of them have a 23 revenue out there. At the end of the day, honestly, we think Cree is the right comp here. You can look at a whole bunch of sort of legacy power semiconductor companies, many of which have still significant multiples. They don't have the same growth dynamic that Navitas does. And one of the things we love about Navitas as an investment opportunity is that while this is game-changing technology, not just for GaN, right, but within the GaN universe, the GaN IC approach, they didn't really wait for the market to come to them, meaning wait for electric vehicle manufacturers to engineer GaN into their products, or wait for solar manufacturers to go ahead and work GaN into the microinverters. They went after the market that has the shortest design cycle, which is consumer electronics. I mean, this is a real business with real revenues, but with enormous growth opportunity because of these additional end markets. Honestly, just the consumer electronics market by itself is pretty interesting from a growth perspective and really puts Navitas out in front of its peers growth-wise. But these bigger end markets, I think, present what we view as a really unique opportunity here. Now, the way we approach, honestly, everything we underwrite, but here in particular, this was done sort of private equity style, which is why, we met Gene and his team in December and announced a deal in May. We hired McKinsey to work with us on the end market analysis in terms of adoption rates and market size. We hired KPMG and their semiconductor team in particular, so not for their accounting work, but for their industry work in semiconductors. They went out and augmented their team with a sort of an industry specialist who personally holds over 200 patents in GaN, primarily GaN on Sapphire, but to really allow us to go deep around this whole GaN IC technology. Because in truth, as capital markets and private equity investors, we couldn't have on our own really differentiated between GaN discrete and GaN IC. So we had a big team helping us with all that. We had FDI helping us with the numbers and with tax. And within that whole process, and I will admit there were times when I felt bad for Gene and the team because we really did go deep. We also talked to between 15 and 20 of their customers. That is not easy to do. That virtually never happens in an IPO underwriting exercise. And even within a private equity underwriting exercise, very few companies are going to let you talk to their prospective customers, right? Where they're still in negotiation around sort of the commercial terms of what their relationship is going to be. And Navitas was open to all of that. And more importantly, the customers that they're talking to were open to it. And I think you're going to see an example of that here in a minute, or a couple examples with the videos that Steve's going to run, and I think even a live discussion. But to have the ability to talk to, an OEM in the electric vehicle world, actually an OEM just in the automotive world, with a power engineering firm focused on that EV market, with a solar player, with players around data centers, it gave us huge confidence in, what these other high growth end markets look like. And is one of the reasons that we think that the discount that this is coming at relative to peers is, extraordinarily attractive. Again, we not only took the time, but expended the dollars and brought in, teams that had real depth of expertise and reach into these end markets to validate, what this Navitas opportunity is all about. So we couldn't be more thrilled to be here. We're really proud to partner with Gene and his team. And I'm going to turn it back over to Steve, I think. I guess I can flip forward to this slide. I'll be honest, I waited to do this because I don't love this slide. This is sort of what I'll call the ubiquitous SPAC valuation slide. Looking forward, as I just talked about a minute ago, comparing ourselves to the 22 multiples of peers, right? And then discounting that back for a year because we're looking at 23 as the valuation year for Navitas. And you can see it's coming at a very, very significant discount to the group. Again, personally, I think that the right, peer here is Cree. And if you focus there, you would see, even bigger discounts. But all of this is just, sort of a visual of, how we sort of think about value. But the truth is, in this particular case, and I'd like to think in all cases of things that we work on at Live Oak, we try to really focus on the underwriting process to validate value and not just the, discounts like this to a peer set. So, Steve, thank you.
Thank you, Rick. And we'll now have some customer testimonials. We have 3 recorded from Lenovo, OPPO, and Prusa, and then we have a live Enphase presentation. Thank you.
大家好，我是 OPPO 副总裁 ，OPPO 研究院院长刘畅。OPPO 的使命是科技为人，以善天下。不管科学技术如何进步，我们始终认为人是所有科技活动的出发点和落脚点。我们也始终秉承利他共赢的理念， 与合作伙伴一起构建开放、共生、共荣的生态，以科技手段实现每一个人对美、想象力和人性的追求。OPPO 与纳威半导体的合作始于2017年，4年间，我们协作为用户提供了很多优秀的产品。去年7月份，我们很荣幸地接受了纳威向 OPPO 颁发的第500万颗 GaNFast 氮化钾功率芯片成功出货的纪念奖杯。这标志着第500万颗纳威 GaNFast 氮化钾功率芯片搭载在了 OPPO 的产品上，成功走向市场。纳威 GaNFast 芯片助力 OPPO 产品实现超越用户预期的体验，与众不同的产品表现。我们欣赏与纳威的配合，打造非常有意义、有价值的产品。纳威的氮化钾器件单片集成了氮化钾 FET 和驱动、控制以及保护功能，差不多是业界率先提供的这种技术解决方案。基于此，我们成功地推出了业界首款高功率密度、超薄丙烯充电器，比以前任何产品都更小、更轻、更薄。丙烯充电器这个技术方向的产品，也有助于节能、耐用、促进环保。我们赞赏与纳威工程团队密切的战略合作所带来的新托普和新产品的战略价值，期待与纳威半导体建立长期成功的合作关系，并祝你们一切顺利。
Hello, my name is Bernhard Budaka and I'm Vice President in Prusa High Power AG and responsible for the product division Power Electronics. Prusa is one of the pioneers in electromobility with over 35 years of experience in developing high-end solutions for electrified mobility future. Our vision is to provide technologies and products with a long-term benefit for our environment and society. Prusa High Power products are onboard charger and DC-DC converters with applications in on and off highway market segments. The efficiency, power density and overall size and cost of our products are driven by the performance of the power semiconductors. Our current product lineup is based on a combination of classical silicon IGBTs and silicon carbide wide bandgap power semiconductors. Prusa High Power is convinced that gallium nitride, or GaN, will enable us to further improve our products. The main advantage of Navitas GaN Power ICs are simplicity of driving, high-speed switching performance and increased reliability and a compact form factor. We have partnered with Navitas since 2020, as for us it is very important to work with cutting-edge technologies in our products. The technological insights provided by Navitas enable us to conduct advanced engineering projects and to ensure that Prusa High Power stays ahead of the competition. Prusa has a focus on sustainable green product innovation, and Navitas GaN Power ICs will be a key factor in reducing the size and the weight of our charger products even further and reducing the CO2 footprint. We look forward to a long, successful relationship with Navitas and wish them well.
大家好，联想致力于成为全球领先的智能产品、智能基础设施和智慧服务的提供商。作为第3代半导体技术，氮化镓可以提高充电效率，缩小充电器尺寸，从而提升客户体验。我们将氮化镓视为联想电源适配器转换的未来方向之一，包括手机、笔记本电脑和数据中心解决方案。我们已经推出了功率从65瓦到90瓦、最高130瓦的充电器，成功应用于 Yoga 电脑及拯救者手机的部分型号上，获得了用户的好评。秉持对更健康、更环保的地球的坚定承诺， 联想制定了未来10年积极的减碳计划，相信在纳威氮化镓功率芯片支持下，更小、更轻、更高效的联想充电器能够帮助到联想成功实现减碳的目标。预祝纳威 IPO 成功。
Hello, control room. Can you help us? Is Mike listening? Can he speak?
I'm here.
There he is. Okay. Since graduating from the University of Auckland in New Zealand, Mike has gained over 40 patents in semiconductors and power electronics. Mike is the chief power architect for Enphase and is in charge of bringing new technology to enable Enphase to retain their market lead as number one in solar microinverters. Mike, take it from here, please.
Thanks for the introduction, Steve. Hello, I'm Michael Harrison. I'm Power Electronics Architect at Enphase Energy. Enphase's purpose is to advance a sustainable future for all by delivering technology solutions that make clean energy more affordable, reliable, and accessible. Enphase is the world's leading supplier of microinverter-based solar plus storage systems with 3 guiding commitments. First, innovation. To continuously innovate and develop new technologies that make energy more intelligent, more connected, and more cost-effective than ever before. Second is quality. It's at the heart of what we do and is the bedrock of the Enphase product design. Enphase solar microinverters achieve an industry-leading reliability of 500 parts per million defect rate and are backed by a 25-year product warranty. And thirdly, responsibility. We are driven by a sense of responsibility towards our planet and our communities. We believe we can have the biggest impact on the planet by pursuing our mission to bring solar energy mainstream. Since inception, Enphase has shipped 34 million solar microinverters, and approximately 1.5 million Enphase-based systems have been deployed in more than 130 countries. 9 DC gigawatts of Enphase microinverters have been installed in solar energy systems, offsetting 20.8 million metric tons of CO2, the equivalent of providing electricity to 3.5 million homes for 1 year. With their net zero program, Navitas is aligned with Enphase's objective to reduce carbon footprint and accelerate the transition to renewable energy using gallium nitride power ICs. After 25 years of development, it's the end of the road for silicon MOSFETs. Enphase has considered both silicon carbide and gallium nitride technology for adoption in microinverter products. Silicon carbide technology can offer a 2x switching frequency advantage over silicon at a similar cost. However, gallium nitride offers more than a 10-fold switching frequency and system cost advantages, making it particularly attractive for the Enphase microinverter application. Enphase has had a relationship with Navitas since 2015. We appreciate the focus on and support of the Enphase microinverter roadmap, with gallium nitride at its core. Enphase believes gallium nitride is a key part of its innovative technology future. Over to you, Steve.
Thank you very much, Mike. We appreciate you being there from Petaluma, and thank you for your input into gallium nitride and Navitas today. Thank you.
Yep. Thanks, Steve. Bye.